Assalamualaikum and good day. So today is 29 of May 2021. Okay, and it's 2:21 a.m. So this lecture is recorded while most of recorded at the same time most of you the students are sleeping. So please make effort later on to watch this lecture. Okay, we start with based on the course information we will cover on chapter 8 sequential MSI. So I will start with synchronous counter first. Okay, this whole chapter should include synchronous, asynchronous counter, ripple counter, 74 times 293 and 74 times 160 devices, basic usage and generating custom counting sequence. So in counters, okay, counters are sequential circuits. Okay, what used for counting pulse. It can be used for frequency counters, time measurement, digital clocks, analog to digital frequency dividers, and waveform. So classified, see, the counters can be classified in several ways. Okay, in several ways. Clocking method. You can see this example. But the most important differentiation between counters is whether they are synchronous or they are asynchronous. Okay, so in asynchronous or ripple counters, okay, they only the first flip-flop is clocked by external clock. Okay, so for asynchronous, only the first flip-flop is clocked by external clock, and then all subsequent flip-flop are triggered by the output of the preceding flip-flop. In synchronous counter, however, all flip-flop are triggered by a clock signal. Okay, so the modulus or mode of a counter specify the count range. For example, a counter with n flip-flop has a count range of 2, 4. Let's say you have a counter with n flip-flop. Let's say n equals to 2 flip-flop. It will has a count range of 2 to the power of 2, which is 4. Okay, for example, a 3-bit counter has a count range of 8 and is known as a mod 8 counter because 2 to the power of 3 is 8, so it will count 8. The count sequence repeats itself when counting up, which is it start from 0, 0, 0 until 1, 1, 1. What is 1, 1, 1? Okay, what is 1, 1? Okay, I use the calculator because just to show you guys. Okay, for easy, what is 1, 1? In decimal is what? In decimal is 7. So it will come from 0 until 7. Okay, so because 0, 1, 2, 3, 4, 5, 6, 7, this one is 8 count. Okay, so when counting down, the sequence start in the opposite, which is 1, 1, 1 until, so this is counting down. Okay, so you start from 1, 1, 1 until 0, 0, 0. It's the same thing. Okay, this one is 0, 0, 0 and this one is 1, 1, 1. Okay, so counter can be built to any size by allocating required number of flip-flop. A counter with n flip-flop has up to 2n unique state. An n binary counter, you see the word binary, use all ever step and count from 0 to 2 and 1. So you have binary counter. So for n bit, okay, for n bit, it will count from 0 to 2n minus 1. Okay, for binary counters. Okay, so n-bit counter whose modulus is less than maximum possible. Okay, you see here the number of states can be less than 2n. An n-bit counter whose modulus is less than maximum possible is called a truncated counters. What does it mean truncated? Because you allow it only count to until certain numbers. Okay, for example, a decade counter or mod 10 counter has 10 state, which is 0 until 9. Okay, 0 until 9, because we only allow it to count 10 state, which is 0 until 9. Okay, here is 0 9. Okay, now we go for without further ado, we go to the what we should be covered, the asynchronous counter. Asynchronous counter are the easiest to build. They are called asynchronous because the clock input of the flip-flop are not all driven by the same clock signal, just like mentioned just now, right? Only the first flip-flop is triggered by a clock. Okay, now basic structure, the schematic diagram and counting sequence of a 2-bit, okay, of a 2-bit binary ripple counter is shown in figure 13.1. Each falling edge on the clock signal causes the flip-flop A to toggle. Okay, you can see because it is each falling edge. Why? Because you see this is inverter, so it will see the falling edge causes the flip-flop A to toggle. Okay, you see we have both to toggle. A 1 to 0 transition at the output flip-flop causes flip-flop B to toggle. The timing diagram counter is shown in figure 13.2. Okay, so you see first from here, okay, you see first this is your clock, okay, and we only start toggle when we have when we consider the falling edge. Okay, so first let's say this is using JK flip-flop. Okay, so you see when this is 0, okay, when 0, and each falling edge on the clock signal causes flip-flop A to toggle. Okay, so this one will toggle because it's falling edge, and then continue, then toggle again. Okay, what happened to the QB? QB is the, okay, what happened to the QB afterwards? When this one is 1, okay, okay, you see initial given is 0, 0, 0. Okay, and then the next we see from the Q2 concept then. Okay, what happened to Q2 after QA? Okay, so here it is toggle. Okay, at this stage, okay, at this stage if you see the clock is depends on your Q. Okay, the clock is depend on your Q. So because this is rising, so there's nothing happen, and when this one is going down, it's clock the QB because it's now it is as a clock for for flip-flop B. Okay, so when this one is rising down, only then we toggle. This one will be toggle from the previous QB outputs. Okay, and then this one just flow through until this one falling edge, then we see toggle again. Okay, means this one is based from this one and this one is based from this one, so this is asynchronous. Okay, only the first flip-flop is connected to the clock, like this one, this clock is actually based on Q2 outputs. Okay, so you guys can see the corresponding here. Okay, I hope the explanation helps. Okay, the counting sequence is like this. Yeah, and then it will restart. Okay, it will restart when we have both QB and Q1 S1. It will restart again to 0, 0. Now, a convenient method for showing state changes in flip-flop in the counter is by the state diagram as shown in figure 13.3. Later on, I show what is state diagram. Okay, each circle represents a state. Okay, so you have a circle, each of them is having a state, represent a state. Okay, so for example here, you can see this is the state diagram for a 2-bit asynchronous binary counter. Why is 2-bit? You can see it's 2-bit, right? So this is what the state diagram. So for the circle containing number 0, 1, for example this one, represent the flip-flop output of what? Okay, represent the flip-flop output of B and A. Okay, arrow shows how the state change, means from 0, 0 until 0, 1, 1, 0 until 1, 1 and 0, 0. Okay, and this one is reset back. Okay, and this one is this one it will reset to 0, 0. Okay, now this is show the 3-bit ripple counter schematic diagram C, B and A. So means that your most significant bit is from here towards your low significant bits. Okay, Now, for example, state 01 is always followed by state 10, and state 011 is always followed by state 00. So you can see it, they are in the loop. Okay. Now, it shows that state cannot go to another state without a direct arrow. For example, state 10 cannot be reached directly from state 00. Like here, right? It might need to pass through 01 only. 00 need to pass through 01, then only then it can be 10. Cannot directly 00 to 10, okay? Now, looking at figure 13.5, we can observe that each flip-flop in ripple counter divides its input by half. If the clock input is 8 kHz, okay, you can see here, then the output of flip-flop has a currency of 4 kHz. Flip-flop B has 2 kHz and flip-flop C has 1 kHz. Just like this, let's say if you have this, if for the 3-bit ripple counter, for example, okay, each flip-flop in ripple counter divide by each input frequency by half. For example, if this is 8 kHz, okay, this one will be 4 kHz. 4 divided by 2, this one will be 2 kHz, and this one will be 1 kHz. Okay, but I think you guys can see, right? The period is increased. So when period is increased, the frequency is decreased. Okay. Now, we can conclude that mod 8 counter is also divided by 8 counters. Okay. So we can generalize to say that an M mod n counter is divided by n counter. Okay, is divided by 8 counters. So we can call this a mod 8 counters. Okay, the other nomenclature for it. Okay, so any flip-flop capable of toggling its output can be used to boot a counter, a T. Okay. Okay. Let's see first here. You can see, right? It count 0, 0, 0, 0, 1, 0, 1, 0 until 1, 1, 0. And then this is 0, 0. And you see this? It is the most significant bits from the left, from the right towards the least significant bits. Okay. Now, this is the corresponding state diagram for a 3-bit binary counter. I think it's straightforward. JK flip-flop will toggle its output when its inputs are fixed to logic 1. I think this one you guys can already learn from previous lecture for the JK flip-flop, right? When we start to have both JK and 1, we will toggle the outputs, okay? D flip-flop will toggle when the output Q1 is fed back to the input, okay? The input. This one is for D flip-flop, okay? But for JK flip-flop, we will toggle once its output when its input are fixed to logic 1. Okay, when we have JK both 1, we will toggle. Okay, whereas for D flip-flop, we toggle when the Q output, when we have the Q output, Q bar is fed back to the D input. Okay, you see there is different. This one is output is fed back to the D input for the D flip-flop. JK flip-flop will toggle its output when its input are fixed to logic 1. Okay, here. Okay, this is JK flip-flop connected to input, connected to logic 1. Now, the problem in major disadvantage of this asynchronous is propagation delay. Okay, propagation delay is because of they are not triggered by a common clock. Okay, so due to this, okay, due to the ripple effect, the asynchronous counter has cumulative propagation delay. Means they are totaling up from all of the flip-flop having delays. Okay, this limit the highest operating frequency of the counter. If a ripple counter has n flip-flop, okay, and t is the propagation delay for each flip-flop, the time for the counter output to be valid, okay, is NTP after the clock edge. This one is the total time. If there are too many flip-flop and the clock is fast, there is possibility that the counter may not have valid output even for a short duration. If your clock is fast, okay, there is possibility that counter may not have valid output for a short duration. The value of NTP must be less than the clock period. Okay. Okay, so you see, this is your clock period. Your clock period must be greater than your NTP. NTP is TP is what? TP is the propagation delay for each flip-flop, and this N is the your number of flip-flop. This is delay for each flip-flop. Okay, and this one should be your clock period. So clock period should be equal or greater. Therefore, the maximum frequency applicable for the counter is, if you have this T, right, F is actually 1 over T. Okay, so your T is given this, so NTP. Okay, and you change it accordingly, so it should be less or equals. Okay, for the frequency, for the maximum frequency. Okay, so this is your F max. Figure 13.7 shows the exaggerated propagation delay in 3-bit counter. Why we say exaggerated? Because we exaggerate so that it can be seen. Okay, so that you can see clearly. Normally it's not that long. Okay, the delay. Okay, synchronous counter do not have this problem, as all output change simulation and high operator frequency may use, because in synchronous they are triggered by a common clock signal. Okay, so we see for figure for 13.7 first. Okay, so you can see the propagation effect in delay ripple counters. Okay, for example, in your clock A, this is the fastest. Okay, what happened is that your B will be a bit slow, just like divide by 2, right? So you can see there's a delay. They will start having delays here, and then further the delay is further accumulate until here. So you find that this is the accumulated delays. Okay, so you see it should be changed here. Okay, however, because of the delay, because they are not triggered by a common flip-flop, is waiting from the other preceding flip-flop. Okay, so that's why we have this accumulated delay. Okay, a side effect of the propagation delay is the appearance of false state, as shown in figure 13.8. This one is the false state. Okay, because the output of flip-flop do not change at the same time, a few unwanted value will appear as the counter changes. Right, for a 3-bit triple counter, okay, changing from the state 011 to 110. Okay, here produce transient of 010 100. Okay, sorry. Here, for example, you can see this is the first count, which is your 011. However, due to delay, you have a false count, okay, of 2. For example, this one, you already experienced delay to flip-flop A, so it will provide some delay. And then after that, because this is delay, flip-flop B is also delay, and flip-flop C also delay even further. So you can see, instead of changing from 011 directly to 100, okay, it will have a 2 transient false state, which is 010 and then 000. You can see right here. Okay, for example, this one is for okay, this one is, I think this one is JK flip-flop and H negative trigger. So this, you see, when this one is negative H, your B should be toggle, right? However, it will not toggle directly because of the delay. It will toggle later on to here. And the same goes for here. You see, when this one is negative H, it is clock for this one. So the C will only toggle to 1 after a period of time. So that's why we have delay. So we have this number 010 here, and then we have 000 as your transient step. Okay. Now, the number of false state depends on the number of flip-flop that change value. Obviously, 3-bit counter exhibit the greatest number of false state when all 3 bits affected. So 3 false or ghost values may affect the operation of other circuit in system if all flip-flop outputs are used to form numeric value. False state can be safely ignored when the ripple counter is used solely for frequency division. Okay, we can ignore this false state when the ripple counter is used solely for frequency division, because only one flip-flop output is used in this frequency division, or if the clock is extremely slow. Okay, is extremely slow. So this is where you can ignore the effect of this false state. Okay, when you have frequency, when it's used only for frequency, or the clock is extremely slow. So we go next is for the asynchronous counter integrated circuits. Okay, so several popular asynchronous counter integrated circuits are listed in this table 13.1. You have 74 times 290, 74 times 293, 74 times 393, modulo 10, 16, 16, counters or chip available 1, 1, and 2, and we have 14 pins for all. Now we go for the next, we go for the first counters, asynchronous counters, 74 times 293 here. Okay, the logic symbol for 74 times 293 is shown in figure 13.9. Figure 13.10 show the internal connection. We will go there. Okay, this one is showing the internal connection, what is inside your 74 times 293, and this one is the logic symbol. Okay, figure the 74 times 293 has 4 JK flip-flop. Okay, it has a 4 JK flip-flop. Can you see? We have a 4 JK flip-flop. 1, 2, 3, 4 JK flip-flop, right? Because you see JK input. Okay. With output Q0, Q1, Q2, and Q3. Q0 is the least significant bit, and Q3 is the most significant bit. Just like I show you. Normally, is like this one is more significant, this one is least significant, going to the left. Okay, but this don't assume it's true for all cases. Okay, but mostly is this is more significant, going to least significant bit. Okay. Now the device can be thought as a two separate section. Flip-flop 0, the one with Q0, is a modulo 2 section. This counter is driven by CP0. Okay, you see, this one is covered by CP0. Remember, this is asynchronous counter. Okay, means that only the first flip-flop is connected by, is triggered by clock, external clock. Okay, so this one is connected to this external clock. This counter is driven by CP0. Okay, which is the clock now, just now. Flip-flop 1 to 3 form a modulo 8 section driven by CP1. You see here, all of this flip-flop 1 to 3 form a modulo 8 section and driven by CP1. You see this one is driven this one. Okay, and then consequently, okay, this two sections can be used independently, mean this one, they can be used separately to function, or they can be joined by connecting Q0 to CP1. If you want them to operate, to be joined, you need to connect this Q0, okay, with your CP1, okay, to build a counter that can go up to 111. Otherwise, it's only 3 bits, right? Okay, so each section changes state on high to low transition on the respective C input. You see, because this one is negative edge triggered, so this one is changes. Okay, each section will change according from high to low transition. Okay, high to low transition, because you see there is negative edge trigger clock. Okay, now here you can see this is the circuits. Okay, so you have CP0, CP1, bar is for clock, and this one is a master reset, and this one Q3 0 is your counter output. Okay, this is your counter output. So if you want them to change just now, evidently, or join is depend on whether you connect Q0 to CP1 or not. Okay, so the whole counter is reset by putting logic high to both MR1, MR2, which is master reset. Why high? Because you see there is no inverted. Okay, so maybe they must be set to 1. For example, if this 1, 1, 1, output be 0, 0 will trigger all of them to be reset. Okay, you see this one? This one is inverted, means they're going to be given 0 for it to be reset. To enable counting to full range of value, both inputs are grounded. Okay, if you want to for this flip-flop, okay, to count for the full range, this M1 and MR2 need to be connected to ground. What happens if we connected to ground actually? Okay, just for simulation, let's say this is 0, right? 0, 0. So 0, 0, we pass here, invert 1, then means it is not reset because it's given 1. Okay, so I think now you understand, right? So we go for the example for easier understanding. Now example, implement a mod 16 counter using 75 times 293. Okay, so this one you implement a 16 mod counters. Okay, now a solution, a mod 16 counter require 4 flip-flops certainly, because you need to count from 0, 0, 0 until 16th count. Okay, start by connecting Q0 to CP1. Why we want to connect Q0 to CP1? Because we want to make sure it can go up to maximum 4 bits, like 1 1 1 1. Okay, maximum it can go. Okay, that's why we need to connect Q0 first to the CP1. Okay, to allow all flip-flops to function as single 4-bit counter. Next, we ground both MR1 and MR2 so that the counter can use all available state. Okay, we ground them because so that to ensure that we can use it to count from 0 0 0 until 1 1 1. So this is the answer. Okay, so if you come from 0 0 0 0, which is 0, 1 1 1 1 is what? Okay, I just show you the calculator so that you can see the proving. Okay, 1 1 1. So you come from until 15. So this one is 16 count. Okay, so next question, implement mod 10 counter using a 74 times 293. So is this 10 counter means it will calculate from 0 0 0 0 until what? Until 9. Okay, so what is your 9? Decimal 9. You don't use calculator in exam. Okay, this one is so that I easily teach you and easily you see the corresponding numbers. Okay, so 9 in decimal. Okay, what is the binary? Is 1001. So it will count only 10 count. Okay, so means that once it reach 1010, okay, which is the 10 count, the 10 10, so it should be restart. Okay, it should restart back to 0 0. Okay, so means that it's only count from this until this. Okay, so we need to disable the, we need to instruct the counter so that it will not consider 1010 and above. Okay, because it should be only counted 10 counts. Okay, 10 counts. So what we do is that, okay, we, like I said, mod 10 and count from 0 0 0 until 1001 and you require 4 flip-flops. Yes, 4 flip-flops because you have 4 digits, 4 flip-flops. We must clear the counter when the counter reach 1010. Yes, it must be clear when it reach 10 decimal. Okay, so this is happen is that when Q3 and Q1 are both high. Okay, so how we going to instruct this to be cleared? Okay, to clear when it's reached 100 is that we connect both Q1 and Q3 to your master reset. Okay, so this is your corresponding answer. Okay, so Q0 is to be connected with CP1 in order to enable it to use 4-bit, and Q1 and Q3 is connected to master reset because once it's reached 1010, we cleared it so that it will start again to count from 0 0 0 until 1001 only. Okay, this is considered 10 count. Okay, so next we go to implement a mod 50 counter using 74 times 293. Okay, this one mod 50 counters. Okay, means it will come from 0 0 until 49 only. So let we see the numbers. Okay, this one is certainly 0, but we see the 49. Okay, decimal 49. Okay, do you see the corresponding binary? is 110,001, and it's of course this 10000. Okay, this is the minimum. 1 2 3 4 5 6 1 2. Okay, so what happened in that in this situation is that, so we have using two flip-flop, means this flip-flop will be your 10 and this one will be your ones. What does it mean by tens and 1? For example, if you have x digit, okay, you have 50, for example 50, so this is your ones. I think you understand this. This is English. I just worry you don't understand what does it mean. Okay, so this is ones, and this one is your tens. Okay, so the first device function is a mod 10 divide by 10 counter, so that for a square wave input. So here this one should be only count until 9. Okay, until 0 until 10, and then so that the for a square input or divide by 10 counter, because it will count until 0 until 9. Okay, because you have here, you see is 9, right, for the 50 count, for enable for it to be 50 count. And then this output is then fed to a second device function as divide by 5. Sorry, my phone stopped instantaneously just now because of low memory, so I have to so I continue where we stopped. So it's 5 counter, right? So here is will be as 5 counter. Why? Because when you want to count 0 until 49, the digit involved is 0, 1, 2, 3, 4. Am I right? Okay, here, so it's only count until 4, means 5 will not be considered. Okay. Okay, so you can see means it will not count for here, for this one is considered as ones. Okay, this one is tens. I don't know if you guys this is English. Okay, the problem is either you know or not, that's all. Like in Malay, this one is nombor perpuluhan. Okay, dan ni is nombor sah. Okay, so if the tens is 0 until 4 and this one is 0 until 9 only, so you can see this one only allow until 4. If it's 5, means it will be cleared and it will be start again from 0 until 49, and after 49 will not go to 50. It will go to 0 again, 0, 49, and then 49 will go to 0, 1, 2, 3 until 49, and then repeat again. Okay, so that's why here is allow only until 4. So what is the digit 4? Okay, the digit 4 in your is what in your, okay, I just want to show to you so that you can see, right, clearly from the digit. Is 4 in the binary is what? In the binary is 1001. How about 5? 5 is the one that we not allow. Okay, 5 in binary it is 101. This why here 101. This why here and here will be connected to the master reset. Okay, this one as well connected to master reset, because at this one it will not be considered. How about this one? It only considered until 9. Okay, because it's count from 0 until 9. There is no 10, right? Because only 0 until 9 digit. Okay, so 10 binary is 1010. That's why 101010. This one be connected to reset. You see, 1 connected to your reset, and then the other one is connected to reset as well. Okay, so okay, then we go to the next one. The next one is 74 times 290 device. Is a asynchronous decimal or mod 10 counter. You know decimal, right? So it's only count from 0 until 9. Okay, because it's count 0 until 9. This is 10 count. It counts up to 1001. Okay, you see 1001 is what? Okay, I just want to show you again. Okay, it's actually 9. Okay, so the logic symbol is shown in figure 13.14. Okay, see first this. Okay, the device is related to 74 times 249 to 74. This is related to 74 times 293 that we discussed earlier. Okay, and shares many pin assignment. However, it has two additional input, which is this one, which is MS1 and MS2, which is stands for master set, which initialize the counter to 1001. If we set this, it will start count from 1001. We start count from 9 if we set this one. Okay, if we set them to turn to active. Okay, so other bit have the same function just like in your AS in 74 times 293. Now the 74 times 290 device consists of two independent sections as shown in figure 13.15. Flip-flop 0, the one with QO as output, is a modulo 2 section. Okay, here. Okay, this one is example of 74 times 290 showing two independent sections. Okay, this one is flip-flop 0, the one with QO as output. This counter is driven by CP not. Okay, this one is covered driven by CP not. You see, this one need to be low, only this one is driven. Okay, flip-flop 1 to 3 form a modulo 5 section driven by CP1. The counter can operate in 3 modes. Okay, for this, so if you want it to operate in BCD modes, okay, the two sections are joined by connecting Q0 to CP1 bar if you want them to operate in BCD mode. Remember what is BCD mode? Is a binary coded decimal. It only counts 0 until 9, right? For the decimal. So to count up to 1001, an external clock will drive CP0 bar. So you need to memorize this condition. Okay, for it to be a BCD mode, we need two sections join by connecting Q0 to CP1, and external clock will drive this CP0 bar. If you want it to operate in biquinary modes, okay, the two sections are joined connecting Q3 to CP0. Okay, Q3 connecting to your CP0, and external clock will drive this CP1. If you want to have them to operate separately, okay, let's say in mode which is the mode 2 and mode 5, both sections can operate independently. Okay, now we go to the example. Okay, implement a mode 10 counter using a 74 times 290. Okay, so it 10 means 10 counter means we count from 000 until 1001. This one is your 9, this one is your 10. Okay, with 0. So the solution is that a mode 10 based on 74 typically use the BCD mode, correct? Yes, because it is binary coded decimal, 0 until 9. So what we do, we will connect the two sections joined by connecting Q0 to CP1. Okay, and then to count up to 1001, and then this external clock will drive CP or not. Okay, so what you can do is Q0 will be connected to your CP1 in order for them to enable for 4 digits. Okay, to enable to count to 1001, and then CP0 will be triggered by the external clock. Next, we will ground all 4 pins MR1, MR2, MS1, MS2, so that the counter go through all state from 0 until 9. So we ground all of this master reset and master set. Okay, so that this so the state will go smoothly from 0 to 9 without interruptions. Okay, so I think this is quite understandable. Okay, you guys can replay the lecture video until you understand. Okay, and of course do exercise so that you'll be able to know whether you understand or not. Next, implement a mode 24 counter using 74 times 290. Both counters should operate in BCD mode. Okay, both counters should operate in BCD mode. So you see, this is 24 counter, means it will count from 0 until 23, 10. So you will have 0, 0, okay, until what is the maximum binary coded decimal that you can have. Means you can have until 23 only. you cannot have 24. Okay, so what is 24? Okay, what is 24? 24 is here is decimal 4. Okay, I just show this so that you can see, right? So 100, this one you will not consider. Okay, this one is your ones, this one is your tens. Okay, tens. Okay, so 2, so this one is 10. Okay, so the two counters are needed to hold the two BCD digit. Connect Q0 to CP1 on both counter so that enable it to operate on BCD mode, right? We need to connect Q0 to your CP1. Okay, Q0 to CP1, both of them. Okay, next, ground all MS1, MS2. Why we want to ground? Because we don't want it to count from start from this. Okay, we want it to count start from 0, right? Okay, that's why we ground both of this MS1 and MS2, so that it's like going up, not from small to high, not suddenly from high to low. Okay, because I think you just now you can see, right? This mentioned it has two MS1, MS2. If we set it will initialize the counter to 1001. Okay? We don't want that. So we ground them, and then connect Q2 on the ones counter. This is ones counter. Okay, which is this position. Okay, this position. Connect Q2 on the ones counter to the MR1. Okay. This I will explain later. You see Q1 connect to this MR1. Both counter, Q2 on the tens counter. Pin Q2 on the ones counter detect the number 4. Okay, so when this one I will explain later. When the counter reaches 24, all MR pin will be pulled high and the counter will start from 000. Okay, just what I told you, it only count from 0 until 23. So we need to enable for it to start count again when it reach 24. Means it's only this. If it's reached these numbers, it will be recount back from 0. So this is 10. This one here, this is your tens, this is your ones. So here means this is 4 will not be considered. Okay, 4 is not considered, and 2 is not considered here. But it must have simultaneously have this value. Because why? Because like this, 23 is still counted, 22 is still counted, 21 is still counted. So it must only reach 24, only then it is not counted. So for example, you see for this 2 is 10. You see 10. So your 1 is connected to your master reset. Okay, 10. However, this one also need 100 at that same time. So 100. So 1 also need to be connected to reset. So this one. Okay, and then you can see this connected to your MR1, MR2. Okay, they are connected. Okay, connected with this reset, and you can see this one is connected with this reset. You can see, right? Okay, so they are like for this 100, we connect it to the both reset MR1, and then this one we connect it to the another reset MR2. Okay, so once it reach this 10 and 100, it will reset. Okay, so with that we finish about asynchronous counter. Okay, we will continue later on with synchronous counter. Okay, so you guys can do the relevant exercise related to asynchronous counter. Okay, don't wait for me to give instruction, because it's better for you to try to do the exercise once you see the lecture video. Okay, Assalamualaikum warahmatullahi wabarakatuh, and see you guys after this. See you guys in the next lecture. Thank you.